I should say that if I don't say that very much, I should say it now. I'm proud, guys. We managed to finish a pretty challenging curriculum at a very reasonable pace. So good on you guys for being able to keep up and seemingly, I think more or less, things went fairly well. All right, last set of notes here. Solving triangles. One of the skills I need for you guys to be able to have is to be able to solve for any side and any angle in a triangle. And I got my picture of good old Telly Monster on there again, and him and his love of triangles. Long story short, a triangle does not just have 3 sides; it has 3 sides and 3 angles, which means there's 6 pieces of information. This is basically the back page on your assignment. I need for you to find all 6 pieces of information, all 3 angles and all 3 sides. Does that make sense? Now, I don't actually care how you solve it. You can use any tool of the following. The first one you can use is Pythagoras' theorem. If that's helpful to you, go for it. Second tool, you should know that angles in a triangle add up to 180. So if you have 2 out of 3, you should know the other one, right? And then the third thing we've most recently learned is the SOHCAHTOA principles. Using any combination of those skills, if I were to give you a triangle or a series of triangles, like say this one right here, where there's a couple of triangles linked, you should be able to find all of the sides and all the angles. So let's do a couple last examples just to kind of summarize our unit. Let's, I don't think I should do all of these ones here, but why don't we pick a couple to try? Why don't we start with the first one up here in the corner? So, can I copy it? No, I can't. I'll just redraw it. So it looked like this. 11 and 6. Okay, so first thought, we have 2 sides and 1 angle. We need to solve for this angle down here, this angle up here, and let's call this an x, a side length over there. Those are the 3 things we need. Your skills are Pythagoras' theorem, SOHCAHTOA, and just knowing that angles and triangles are 180. So how can we solve for x? Pythagoras' theorem should work. Why don't we start with that? So you don't have to do that one first, but you could. You could say that 11 squared minus 6 squared will be equal to this x squared over here. So 121 minus 36. Should be able to do this with a calculator. That's 85. What do I do next? Square root it, yeah. I've said that you're allowed to go to the nearest tenth if you want. So if you square root 85, I get x to be 9.2. Because of the fact that when you round, sometimes when you use the number later and later and later, it kind of causes a little micro errors over time. I'll usually give you a little bit of leeway. So like maybe I could let you get away with 9.3 or 9.1, kind of depending on how rounding works. So, okay, we got this side right here, 9.2. All right, next one, we got to figure out the angle. It doesn't really matter which angle we solve for. First, why don't I solve for this one over here in the corner? If I solve for that one in the corner, I actually have 3 different ways I could solve for it. I'm going to try it all 3 times just to prove that it works. I could use sine. Well, sine is opposite over hypotenuse. From this angle right here, who is the opposite? Yeah, so I'll go 9.2 over hypotenuse, 11. That should work. But I could get the exact same answer a second way. I could have said that cosine of theta is equal to the adjacent over the hypotenuse. The adjacent would have been 6 over 11. That could have worked as well. I could have done the third way. I could have said that tan of theta is opposite over adjacent. Any 3 of these things should work and give me basically the same angle minus a little bit of rounding. How do you get the angle by itself though from here? Do you just type in sine 9.2 over 11? What's the right vocabulary? What do you call it when you need to undo this? Yeah, I call it a sine inverse. So if you have your calculators, here's 3 ways, all should give you the same answer. If you were to inverse sine 9.2 over 11, got about 56.8, let's call it. But let's say you didn't choose sine. Let's say you chose cosine. It should still work if you did the cosine of 6 over 11. See how it's more or less the same number, minus a little bit of rounding. And if I were to do it even one more time, an inverse tan, 9.2 over 6. See how, again, it more or less gives me the same number, 56 point something. Well, why is it slightly off? Can you guys figure out why there's a slight difference between them here? Go for it.
The rounding of 9.2.
Yeah, this number of 9.2, it wasn't actually 9.2, it was something more intricate than 9.2, right? So because we use 9.2 just rounded right here, it's slightly off. But at the end of the day, hopefully you guys would agree, I did this 3 different times, and it looks like they're more or less averaging to be about 56.8, give or take. If you said 0.7 or said 0.9, I'd be okay with it. I'm okay with a little bit of rounding issues.
Provost, can you please come to the office? Test Provost, please come to the office.
If you take my physics class and my chemistry class, I would want you to be more exact. I wouldn't actually want you to use just straight up 9.2. I'd actually want you to use all of the digits possible. I'm actually working. There you go. So like when I square rooted 85 to get that 9.2 number, it would be best to actually use that whole number and use like the inverse sine of 9.219544457 over 11. That would be best to do it like that. Anyways, does that make sense how you actually have 3 different ways to tell you that the angle was about 56.8 or 9 or whatever you rounded it to? You could do that again for the other angle up here, or you could just know, well, don't angles in a triangle add up to 180? So 180 minus 90 minus 56.8 or 9 or whatever you pick there means this one should be 33.2. That makes sense. And now we have 1, 2, 3 sides and 1, 2, 3 angles. We've solved the triangle. Turn my notification off for a minute. Should we try another one? Yeah? Well, let's try one more. We'll try one more off this slide, then we'll try the next slide. So let's pick the second one here. You guys can try the rest later if you need practice. So the second one here, I give you an angle. 9 there, that's 9, and I give you 32 degrees there. So right off the bat, we actually have 2 out of the 3 angles. If you have 2 out of the 3 angles, shouldn't you be able to find the third by subtracting from 180? If that's a 90 in the corner there. So, calculator. 180 minus 90 minus 32 means this angle here is 58 degrees. Alright, that's pretty straightforward. Well, now I've got 2 different sides I don't know. I don't know this side here. I'll call that one X, I guess. And I also have a side right here I don't know. Let's call it Y. I don't really care what letters you use. Just pick a letter or a symbol or a smiley face or a squiggle. Can I use Pythagoras' theorem? I need to know 2 out of the 3 sides. So I have to use one of my SOHCAHTOA kind of things. I'll just pick one. Why don't we make 32 be the angle we use? I have to pick one of them to be, so let's just go for 32. Let's say that the cosine, no, actually cosine's the one thing we actually couldn't have used. Why don't we say the sine of 32 degrees, that's supposed to be equal to opposite, well, what's opposite the 32? 9. 9 is opposite the 32. Over the hypotenuse, which one's the hypotenuse? Actually, y. Y. Algebraically, how do you get y by itself? Well, yeah, you kind of flip these guys around. Y goes up over here, and sine of 32 goes on the bottom. There, that should work. Is that the only way this could have worked? No, there's other ways you could have done this. Let me just try one more time here with the second option. What if I had made my angle be 58 over here? Well, then I could have done, like, say, the cosine of 58 degrees. Y right here would be the hypotenuse again. But now this 9 over here would have been the adjacent. That could have actually worked the same way using a different ratio. So I don't actually care which one you pick, so long as you pick one of them that works. Right? If this is the angle we have right here, this would have been the hypotenuse. That would have been the adjacent. Yeah, it's got a calculator here. If I did 9 divided by sine of 32, it tells me that this side right here is 16 point, well, let's round it, 17.0. If I had done this one right here, it would have been 9 divided by the cosine of 58. And that also could have worked. It would get you the same thing either way. If you're in agreement that this side right here is 17, you have a couple options. You could use Pythagoras' theorem. You could go 17 squared minus 9 squared and solve that. You could pick another identity and go with, let's say, 10 of 32. 10 of 32 would be opposite over adjacent. And use them. Flip these guys around and go x is equal to 9 over tan 32. There, this side is 14.4. Let's say you did Pythagoras' theorem though. It should still work. Watch this. That's okay. You did 17 squared minus 9 squared, and you square rooted the answer. That's still 14.4. Let me do it another way here. Let's say that you wanted to work with this angle right here. So that's the opposite. You could have done the sine of 58 degrees. So here's our angle. This is the opposite over the hypotenuse. And you could have just times the 17 up and did 17 times the sine of 58. Still 14.4. One of the cool things about solving triangles then is that there's no right way of solving it. There are wrong ways. You can do it incorrectly. But when I make my answer key here, I'll solve it one method. And if you solve it a different method but you still get the same answer, I don't care. If you want to use Pythagoras' theorem, try that. If you use tan and it works for you, awesome. If I use cosine and it works for me, who cares, right? Like it's potato, potato. Does that make sense? So that's why in my first slide here, I like to point out that really you have tools at your disposal. I need you to know how to use them. All right, last few examples. The harder type things I'm going to have you do is where I give you multiple triangles together. So for one like this, see how there's this blue line right to the middle of it? That common line is the same on like the triangle on this side as it is on the triangle on this side here. So you can kind of use like one triangle to solve for the other one. Let's give it a try. If this is 90 and that's 60, we should be able to find that angle right there. How? If this one's 90 and that one's 60, that one's 30. How did I just figure that out? Yeah, adds up to 180. There we go. Okay. More than that, if this is 90 degrees right here, hopefully this is kind of intuitive, but shouldn't this one over here also be 90? Because shouldn't like this line kind of add up to 180 degrees? Shouldn't a flat line be 180? So it means if this is 90 and that's 40, you should actually be able to tell me this angle here is 50 degrees. Because 180 minus 90 minus 40 is 50. So like we're already a good chunk of the way started. Okay, well let's just start labeling for things we don't know. Why don't I start solving for this side right here? And there are so many ways I could solve for this side right here, but I'll pick one. Let's pick the 40 degrees. Compared to the 40 degrees, this would be the adjacent side, and 21 would be the hypotenuse. So if I said cosine of theta is adjacent over hypotenuse, I could say cosine of 40 is x over 21. I don't have to do it this way, but this way works. Here's your adjacent to 40. Here's your hypotenuse. If I want to find what x is, I just times up the 21. I got 16.1. What do you need? Oh, get what you need. Does that make sense so far? Oh. Well, let's look for this side right here. Why don't I call it y? I don't really care what letter I pick for it. There's so many ways you can solve for y. You have two sides on the triangle. You can use Pythagoras' theorem. That'll work. You have any angle and any ratio. It doesn't really matter. Why don't I pick the 50? Just, I don't know, because. Based on this 50 degrees right here, the y would be the adjacent, and the 21 would be the hypotenuse. So you could say that cosine of theta is adjacent over hypotenuse. Cosine of the 50 degrees, this 50 right here, the adjacent would be y, the hypotenuse is 21. Let's go times the 21 then. 21 times the cosine of 50, I get 13.5. Is that the only way you could have solved for it? No. Here, let me just prove it to you otherwise. You could have taken 21 squared and minus 16.1 squared. You could have used like Pythagoras' theorem on the triangle there. And look, you still get 13.5. You guys still with me so far? Okay, well at this point here, that 13.5 is on the other triangle. So let's do another one here. Let's use the 30 degrees right here. Actually, let's use the 60. Compared to the 60, this would be your opposite. And that would be your hypotenuse. So you could say that sine of 60 is normally its opposite over hypotenuse. Here's your 60. Your opposite would be 13.5. And your hypotenuse, let's call that z. Another letter to use here. How do I algebraically get z by itself? What do you do? Flip those two guys around, right? So make z be equal to 13.5 divided by sine 60. Which apparently is 15.6. You could use Pythagoras' theorem again to try to solve for, I'm running out of letters. Let's make this be smiley face. What's the letter after Z? I could use, why don't I use tan? Tan of 60 degrees would be the opposite. The opposite of 60 would be the 13.5. The adjacent to 60 would be the smiley face. So if I want to get smiley face by itself, I just flip these guys around. 13.5 divided by tan of 60. 7.8. I think I've now solved for everything. Could use Pythagoras' theorem. 15.6 squared minus 13.5 squared. Square root the thing. Yeah, same thing. See how this 7.8 and the 7.8 are slightly off though? The only reason they're slightly different is because like I've been using rounded numbers, right? So, but I mean they're pretty close. That'll be good enough for right now. Makes sense? You okay on this? Or you said your hands on your head. Okay. But it's not the math that's the problem then. Fair enough. All right, let's try one last example, then we'll be done. Last example of the year. Your enthusiasm is mediocre. Yeah, there we go. Okay. Let's try one more. Alright. So, where's a good place to start? Anyone see any good place to start? What's that? How about the angle up here? Did you find that angle up there? How'd you figure that out? You're right, it's 42. How'd you figure it out? Yeah, if you have 48 and 90, 42 is the leftover one. That's a pretty easy principle to work with. What about this angle right here? Because, well, same sort of logic, right? 51 and 90 plus 39 add to 180. That's a good place to start. Which side should we start for? Why don't we call this one X and we'll start there. You have options. You could use sine, you could use cosine, you could use any of the angles you want. Why couldn't you use tan to solve for this X side right here though? You know, something like tan would not work for solving for this one. Yeah, tan is opposite over adjacent, and this is neither the opposite nor the adjacent, so that doesn't help. So we just need to pick something that works. Like, let's just go with sine. Sine, sure, let's go 42. Sine of 42 would be the opposite, 86, over x. So to get x by itself, 86 over sine 42. 86 over sine 42. X is 128.5. Just because I want to show you can do it a different way, why don't we try doing, we could have done the cosine of 48 degrees. The cosine of 48 degrees would have been the adjacent over the hypotenuse, which would have been 86 divided by cosine 48. Same thing. Two different ways, same thing. I don't care which one you pick, just pick one of them. Let's call this side over here y. Why don't I use Pythagoras' theorem this time around? That should work. To get y, if I did 128.5 squared minus 86 squared, and I square root it, that's all right. Square root the answer. Then this side over here is 95.5. It's not the only way I could have solved it, but it works. Then for the second triangle, the 95.5 is the hypotenuse. It means that I have to use sine or cosine. I can't use tan because I don't have a hypotenuse in tan. So why don't I use cosine? Cosine of 39 degrees would be the adjacent. What's the adjacent here? That would be here. This will be the adjacent. Z would be the adjacent over the hypotenuse, and the hypotenuse we just said was 95.5. So if you take 95.5 and times it by the cosine of 39, we now know that this side here is 74.2. Last side, I mean this little side over here, smiley face, I don't know, W-A, I don't know, pick a letter. I already used X, I used X over here. You used X twice, I guess, but that gets confusing. X2. Yeah, that's a good point. That would be a bad idea. For this one right here, why don't I say tan? Tan of, let's say, 39 degrees would be the opposite. Well, the opposite of 39 would be my smiley face. My adjacent to the 39 degrees would be the 74.2. Times 74.2 up there then. Tan of 39 times by 74.2. There, this side here was 60.1. I didn't have to do that. I could use Pythagoras' theorem. I could have done 95.5 squared minus 74.2 squared and square rooted it. Yeah, look, it's still 60.1. So here's what I need from you guys. I don't care how you solve. You can use Pythagoras' theorem, you can use sine, cosine, tan. Pick your whatever you like best. Okay? You should know how to do all of these skills. But on a question like this, I just want you to find me all the sides, all the angles. You're either right or you're not. Right? There's really one of the things I said to some kids earlier is that although trig is difficult, don't get me wrong, it's not necessarily the easiest thing in the world to do. There's not a lot of work to it. Pretty much the only work to trig is like you just write out one statement and you solve that statement. It's not like algebra where you do this and then this and then this and add to that side, right? Like most of it's just done in one step. So as long as you can wrap your head around what that step is, that part's not the hard part. Right? There's not like a page worth of work here. I just kind of have chicken scratch all over my page here. So long as it's clear though that you found this side, this angle, this side, and that side, so long as you can get me all the sides and all the angles, we're good. Questions, comments, concerns, conundrums, etc. Does this make sense? You're good? Okay, one last summary, then you guys take a quick break here. So you got 4 things to do, right? There's an assignment. There is a project, which by the way you can do with the partner if you'd like. There is a quiz, which you can write anytime next week, Monday to Thursday, and a unit test, which you can write anytime next week, Monday to Thursday, I guess. I don't really care when. Try to get it all done before Christmas. No. And then one more thought. If there's anything else that you still need to do that's late, or like you know that you haven't accomplished something, you haven't finished it, can we work on that before Christmas as well too? So that if you have to hand something in late, I can get it all marked over the holidays. Ideally, you guys should have all 5 progress logs done before Christmas, if possible. I'd like to finish that if we can. If you don't have a progress log done before Christmas, it's either because you haven't done something, or because I still have to mark it. Okay? So, sound good? Cool. Okay, take a break as you need.